You got it? All right. He has some experience, so I'll begin. Holy Father, we thank you for this opportunity we just have to meet together to study your creation. Pray that you'd guide these students as they work on this course this semester, that you'd bless their work, and just I pray that they would glorify you in what they do. That as they do their homework and just work on studying for this course, it not just be for the sake of a grade or various personal things, but it also, Lord, be for your glory, that they would just seize the opportunity to do everything that they do, Lord, for you. In your name I pray, Lord Jesus. Amen. Let's see here. So this is my webpage, if you didn't know. Have I posted a link to this in an announcement or something? I have? Okay. I lose track of what I've done at this point. And I mean, so my laser. So as you can see, here's a link to our course page, Differential Equations. I click on that. Oh, stop that. Here's the course planner for this semester. I'll click on that in just a second. These are missions 1 through 8. I collected these like last year, and I posted solutions. So there's still good problems to work out, but I'm not going to collect them because I've already posted solutions. So the structure of your course is a little bit different. So this is the course planner, which is essentially, it's like a syllabus except with only useful information. Let's see here. So first of Mr. Excellent. Okay, yes. Let's see here. So like this is recommended homework. All right. So I'll steal a phrase, a turn of phrase from my brother. He says, the students ask him, "You mean the homework's recommended?" He's like, "Does that mean I don't have to turn it in?" And Bill's like, "Yeah, you don't have to turn it in." They're like, "So it's just recommended?" And he's like, "Yeah, it's recommended. Like, I recommend you pass this class." You know? I mean, so you should think of it in that way. If you don't do the homework, you won't learn the math. It's just kind of funny how that is, right? You're in differential equations. You know this already. You've somehow gotten through calculus 1, 2, and 3, right? So some of you in a good way, some of you through community colleges in the summer. Who knows? There are many routes. Depends where you're from. But anyway, you're here, so you probably know enough to do this course, but it cannot be done without doing the work. All right, enough about that. You guys know this. This is recommended, though, which means that I recommend you do it. I will not collect it. By the way, solutions are already posted to this homework, like I said on the previous page, right? Now, should you do the homework with the solution in front of you? Obviously not. Should you do the homework while checking Facebook? Obviously not, right? I'm sorry, Facebook, whatever it is you guys do. I don't know. There's this Tinder thing and I don't know. Do we do that? No? No, it's not. There's no like Christian Tinder or something? No? Okay. I don't know. I don't keep up with these things. I mean, I went to this talk about Generation Z and such, but you guys aren't part of Generation Z. You guys are the millennials, right? I mean, allegedly. But I refuse this term. It offends me deeply when we have these meetings and talk about everybody like they're all the same. Like to me, it's deeply un-American. You guys are individuals. You make your own path. You can succeed or fail at this course. It is up to you. If you're not able to fail, you're not free. I think this is lost in our discussion somehow. Like, everyone shouldn't fail. If everyone can't fail, no one's free. Failure is part of freedom. So you're free in here. Not really what I was trying to, that was not entirely what I was aiming for today, but it was not really what I was trying to emphasize. I think everyone here who does the homework will pass the course. It's very likely. Okay. And when I say does the homework, I don't mean copy my solution from a PDF onto another piece of paper. It's not doing the homework. Doing the homework is reading the problem, attempting the problem without distractions and without help until you understand the method for yourself, right? So test 1 will cover all of this stuff. Basically first order, nth order problems, homogeneous or otherwise. And then test 2 covers this material, give or take. Then there's a PDE project, which is due. And then there's reading day. It seems kind of sad that we just devote one day for reading, you know? I mean, I would think we should devote more. It's a joke. Let's see here. I shouldn't have to tell you it's a joke, though, I guess, but rough crowd, I guess. Let's see here. Test 1, Test 2, 200 points, 200 points. PDE projects, 100 points. Quizzes and participation, 200 points. Final exam, 300 points. All right, so basically what's going to happen in here is I'm going to give you quizzes as we go on. The quizzes will be shockingly based on whatever examples I go over in here, right? And the missions that I recommend you finish by that time. So you kind of have to follow the course, right? When I get through a certain technique, you might expect the next time I have a quiz, it might be about that technique, right? I'm probably not going to quiz you on stuff I haven't covered yet. That would be mean. So it's unlikely. But then again, I'm sufficiently disorganized. You never know. I mean, no, I'm sorry. Take that back, because then you guys are going to like believe me, and then when I have course evaluations later, you're like, instructor himself said he was disorganized. It was a joke. Okay. So I think you guys seem like you're with it. I can make jokes, right? Okay. Okay, good. Good. Because, I mean, I once had a college algebra class. I told a joke I always tell at a certain point, and like, no one laughed. And then I realized where I was. Oh, we can't teach that course anymore. It's not. It's been relegated to the Emporium. So, but so I don't really have contact with that segment of the population at Liberty anymore. I should always remind myself that I am talking right now to the elite of Liberty. Right? You guys are the creme de la creme, mathematically speaking. You can add fractions. You can divide fractions. You probably can multiply fractions. You know, you can do most of basic algebra, usually with the right laws. If you apply a wrong law, you usually do it consistently, at least that, you know. I do see lots of new techniques of integration in this course when we start getting into things. But anyway, any questions before I waste the whole class on this nonsense? It's pretty simple. We're going to have quizzes, and that's pretty much it. And then there's a test, 2 tests, and there's the PD project. Yeah.
Will the quizzes be consistently on like Tuesdays or Thursdays?
The quizzes can happen anytime. There might be a quiz Thursday, for all I know. Depends on how busy my week is and whether or not I want to make a statement. I don't know. Do I want to make a statement? No? Okay. Tell you what. The first quiz will be next Tuesday. Does that feel better? Like, now I can procrastinate my homework till Monday night. But in the interest of demoralizing your procrastination, they will be either Tuesday or Thursday in the future. I'm not going to. We might have a quiz every day. It just depends. But we will have quizzes. Okay. And they will probably usually be, I don't know when they're going to be. They might be in start class, might be in class. I want to keep it interesting in here. So if you hadn't noticed already, I have lecture notes that are, there's a lot in here. I would recommend that you look at these. I would also recommend that you save a local copy. I mean, the internet here is relatively fast, even so, right? Yep. All right. So there's a reason for that. There's like 212 pages? Okay. So today, basically, I'm going to be talking about this stuff, all right? I have gotten to the point where I don't even talk about this much because it kind of explains itself as we go, right? This chapter basically tells you a differential equation is an equation that involves derivatives. And then it defines things like order of the differential equation. What's a linear differential equation? What's a non-homogeneous? What's a homogeneous? All these kind of terminology. We'll pick those up as we go along. So I'm more and more of the opinion that covering the first chapter in class is boring. So I'm going to skip straight to chapter 2 where it gets interesting, and hopefully you can appreciate some methods. So with that, unless there's a question, I'm going to get into the material. I inadvertently didn't cover any math in Calculus 2 yesterday, and I still feel kind of dirty about it. So it's like, need to recover some math. I mean, if we don't cover math, what is this place? See here? Where was I? I think I can put this away. I really, I probably should, well. Did I show you guys my new phone? I'm like a billionaire. It's got buttons. See? When I'm done with a call, I do this. It feels amazing. The glass on my other phone broke. Anyway, I have no intention of fixing it. Okay, so first order differential equations. Let's get right into it. Some of these you've already solved. Where? Calculus 2 maybe? Right, we did separation of variables and integrating factor method in Calculus 2 if you took it here. Or you should have done that. Anyway, we'll go over it again. So generally speaking, first order differential equation looks something like this. dy dx equals to f of x comma y. All right. This is a first order differential equation. If you also supply an initial condition, if you say, okay, I also want, say, y of x naught to be equal to y naught, if we add to this y of x naught, say, equals to y naught, suppose x naught and y naught are fixed given values, these two things put together is what's called an initial value problem. All right? So I usually focus on just the black here, but we can always tack on an initial value and see if you can solve the initial value problem. So the question then is, how do you solve differential equations like this, right? What are the techniques? So there are really three major techniques. I'll share them with you today. Technique number one, separation of variables. All right. Separation of variables. Basically, this is a very close cousin to U substitution in calculus. I don't think I need these. Two, I forget I have them on sometimes. Math has made me blind. Or my children. I should blame math. Let's see here. Integrating factor method. All right. And three, the method of exact equations. All right. These are the three major methods. Past this, I mean, there is, I always say these are the three major methods, and I say, okay, fine. Four is substitution. So substitution that's less of a method and more of a ninja way. I mean, it's vast. There are many arts there. It's much more open-ended, what I'm saying in number 4. So let's get right to it. Example 1. dy dx equals to xy. Right? This is a first-order differential equation. I'd like to find the general solution. So that's our goal. Problem, task, if you like. Find general solution. So how do we do it? Well, this is amenable to separation of variables because you can see the sort of the f of x, y as just being a product of functions of x and functions of y. So the label of the technique kind of explains to you what you do. We say, okay, so that's dy over y is equal to x dx. At this point, we've separated variables, right? And then what you do is you integrate both sides, right? If you want me to be a picky mathematician type, what we're really doing is we're applying the chain rule, and we're using the theorem of U substitution, like integrating by U substitution. So I'm doing an indefinite integral, which of course is going to give you like natural log absolute value of y is equal to 1/2 x squared plus a constant. Now you say, well, why did you add a constant on one side and not the other side? Well, fine. I mean, if you like, I could add c1 to one side, I could add c2 to the other side, and then this c would just be c2 minus c1. And it's the same freedom in the formula, right? Nothing is lost by just adding a constant to one side, logically. So at this point, you could say, okay, I'm done. That's it. That's the solution. And some people would disagree with me, and they'd be wrong. I'm just kidding. It depends on who they are. So this is what's called an implicit solution. The reason it's an implicit solution is that I haven't solved for what? I have not solved for y. Right? So implicit solution gives you y and x, and they're related by some equation. Okay? I'd like to still think this is a solution because there are lots of differential equations that give you implicit solutions that you just cannot solve for y. Lots of equations that you can face where y is intertwangled, sorry, technical term, with x in some sort of way where you can't solve for y algebraically. And yet, the equation gives you some relation between them. Right? Okay. So what's the explicit solution here? We can solve for y, right? So exponentiate both sides. I get the absolute value of y is equal to e to the 1/2 x squared plus a constant, right? Properties of exponents, that's e to the c, e to the 1/2 x squared. Right? But this says y is equal to plus or minus e to the c times e to the 1/2 x squared. Right. So, all right. It gives me no joy to write this. I mean, we should try to clean things up if we can. And so I say, okay, fine. So the explicit solution here is y is equal to something like k times e to the 1/2 x squared. And there you go. That is the general explicit solution. All right? Something kind of neat happened. And I could say for k, any real number, right? Any real number. Can anybody tell me what's wrong with that? Saying k is any real number. Like, what is wrong with that on the basis of the red arrow? Like, why is that bogus? What's not possible for, what can k not be? If k is equal to plus or minus e to the c, what can k not be? Yeah, k could not be 0. E to the c is positive. That's plus or minus a positive. It's not 0. E to the c is not 0. So what right do I have to say k is equal to 0 as a solution? You had to go back to the start, right? If you go back up in here and you look at d dx of the 0 function, is that equal to x times the 0 function? If you differentiate the constant function, what do you get? 0, right? Doesn't change. And x times 0, 0. Does it work? Yes. And so I'm introducing you now to the idea of what a solution is to a differential equation. A solution to a differential equation is a function, or possibly an equation, that when you plug it into the differential equation, the equation is true. In other words, the differential equation is a differential consequence of the function or equation, which I'm saying is a solution. So the reason that 0 should be included is because I go back to here and it works. Now, why did we lose 0 in this technique we just did? Why was 0 lost? Can we understand that? I mean, I put it back here by just relabeling this as k, and then I said, k could be anything, right? Of course, logically from here, that's not true. Why do we lose 0?
Because there's no way that you can make 0 with e to the c.
That's true, but why did that happen to us? That's also true. I can't take the log of 0, but why did that happen to us? What's that?
Does it create like a discontinuity in the
That is probably also true, but why did that happen to us? In the technique, like what step did we lose 0? Right, yeah, exactly, right there, where we divided by y. This is not allowed if y is 0. So surprise, surprise, our solution doesn't have y equal to 0, right? That make sense? So this is true of all our techniques. When you make some step which disallows a certain algebraic feature, you may lose that feature in your quote-unquote general solution. Right? So every time you make a feature, make a step like this, it comes with baggage. Right? You're basically, once you do this, you have to set aside in your mind, oh, wait a minute, I got to check y equals 0 later and see if that's a solution, you know? Now, these problems are forgiving. A lot of times it comes back to you by just relabeling, but that's an accident. So y equals 0 is what's called an extraneous solution to the method, all right? Would you guys like an application? I mean, not for a job, but let's see here. How about this? Physics. You guys like physics? I know you guys like physics, right? How about acceleration equals to g? And also being, oh, fine, minus g. Happy? dv dt. So v is equal to dy dt, right? So we can try a couple things here, right? We could task, here's some tasks for us. Find v as function of t. Find v as function of y. So let me start out with the easy one. Function of t, right? So we have minus g is equal to dv dt. I'm going to do this separation of variables style, which is silly, of course. I mean, you could just integrate both sides, right? But maybe it's kind of fun to look at this as separation of variables. So this is dv is minus gdt, right? And let me throw out something else to you. If you want to work in initial conditions, you can integrate over appropriate bounds. So if I integrate v from, say, v naught to vf, I should integrate minus g dt from t naught to tf. Theoretically, I'm using the U substitution theorem, which says that when you change variables, you must change bounds. But it's also physically natural, right? Matching velocities with matching times. And then, of course, this gives us vf minus v naught equals to minus g times tf minus t naught. Lo and behold, vf equals to v naught minus g times tf minus t naught. Now, usually, so we can, if you let the final time just be time, then that also gives us the velocity as a function of time is v naught minus what? Minus g times t minus t naught. A lot of times in physics, of course, we work with this formula with t naught set to 0. But there it is. Of course, you could derive this with like the fundamental net change theorem from calculus, right? The integral of the derivative is just the change. But it's fun to look at it from a separation of variables perspective. Now, we're done now with this part, right? I have presented the solution in terms of initial conditions this time, right? I would say this is a general solution. I mean, I don't know what you want. Here's the language gets a little fuzzy. I mean, I've stated a solution that works for arbitrary initial velocity, right? So, okay. I mean, sometimes you're asked to state the solution in terms of initial conditions. And the initial conditions may or may not be given as specific numerical initial conditions, right? I mean, your boss should be happy with you. If you solve this problem, you've solved it for all possible initial conditions. If you put numbers in, well, I guess there's more job security in putting numbers in, right? Because he's got to come back and ask you to do it again. If you give him this, then you can just fire you. He's already got the formula, right? I mean, I don't know. Part 2. So what if we want to find v as a function of y? So here, I need to change to y. So what I do is a trick. This is dy dt, dv dy. Now this makes sense because we're in one-dimensional motion. So what is dy dt here? Velocity, right? So this is v dv dy, which gives me joy to say. And of course, I'm assuming that g is a constant throughout, right? You guys didn't ask me, but it is assumed g is constant. If g was a function, then this would be a different problem. Now, this is a problem for separation of variables, right? Honest to goodness, because this, we separate variables, we get what? We get minus g dy equals to v dv. Right? This is something a Calculus 1 student might have more trouble with. Right? This first semester calculus, easy peasy, right? Over here, so much. This, so I integrate from y naught to yf, y naught, and integrate from v naught to vf, all right? Of course, the integral of g dy is just minus gy, so I get minus g times yf minus y naught. And on the other side, I get 1/2 v squared, evaluated from v naught to vf. What's that give me? 1/2 vf squared minus v naught squared, right? And so there you go. This gives us vf squared equals to v naught squared minus 2g yf minus y naught. Of course, this is the infamous what? The timeless equation, right? There's a specific set of 231 problems which are designed to force you to use this equation. Do you know what it is, though, really? Multiply by m, divide by 2, right? What happens when you rearrange terms? What is the timeless equation? It's conservation of energy. So sometimes substitutions have deep physical meanings as well, right? Changing velocity to a function of position gets you to energy conservation in this way. All right, so that's separation of variables. We could do some more problems, but that's a good start, right? Showed you an application. I don't always do this, but I thought it'd be fun. I may be reevaluating that. Let's see here. Any questions? Yeah? No? All right. So we go to what, 12:45? Okay. I see. The joke never gets old to me. Let's see here. All right. So next on our list is integrating factor technique. Now, integrating factor technique, these methods, by the way, are not mutually exclusive. But, well, anyway. So here's the problem that this one solves. If you have a differential equation that has the following form, dy dx plus py equals to q. This is a first order linear differential equation in standard form. All right. Sometimes these problems come to you with the terms rearranged and something multiplying dy dx or something, so you have to like, wait a minute. If I isolate dy dx and write it like this, it's just one of these guys. So sometimes they come in disguise. It could be something stupid like 2x dy dx plus y equals to e to the x, something like that. And be like, that's also a first order linear differential equation, but it's not in standard form, right? To put it in standard form, I go right? For example. Okay. Now, so what I'm going to do here is I'm going to work an example, and I'm also going to show you the general technique for solving them. I'm going to do it side by side. I think it helps to understand the derivation. If I just do the derivation on its lonesome, it kind of it's not as much, not as useful. So here's the problem we're going to solve. Pretty simple one. Pretty important though. Dy dx minus y equal to e to the x. All right, so here it's assumed that p and q are continuous, all right? Let's just say nice. In fact, they could be piecewise continuous. As long as I can integrate them, we're okay. So here's the technique. You invent this thing called the integrating factor, which I usually use I for in here. It's the exponential of the integral of p dx. The neat thing about this integrating factor is if you calculate the derivative of it, dy dx, what does it give you? The integral of, the derivative of an exponential is the exponential, right? And then you have to chain rule. What's the derivative of an antiderivative?
They cancel out.
They cancel out, right? So it just leaves you with p, right? So we have then that dy dx is equal to p integral, rather p e to the integral p dx, right? Which is what? What we just defined it right there, right? The exponential of the integral of p dx is I. So this is pi again. So dy dx is p times I. All right. So step one is to calculate the integrating factor. All right. That's the integrating factor. And then step two is to multiply, let me call it star, by I. So I'm going to call the differential equation we're working on star. So I have I dy dx plus IP y equals to IQ. All right, so let me take a break here before I go on with the general derivation and stop and what's the integrating factor for my example over here? Which I guess is example what? 3 for counting. So here P is what? What's Q? I'll do Q. Q is e to the x. What's P? -1, right? Not too bad. So what's I? Exponential of the integral of -1 dx. AKA e to the minus x, right? Some of you are silently shouting in your mind, Why didn't you add a constant? You should add a constant. It's an integral. Fair enough. But I'll explain to you why that doesn't matter in just a second. So, tell you what, I'll add a constant just this once, just to be nice. Plus c. You happy? All right? So this is e to the c, e to the minus x. All right? Now what am I going to do? Step 2, multiply the equation by the integrating factor, right? 2. So we have e to the c, e to the minus x dy dx minus e to the c, e to the minus x times y equals e to the c, e to the minus x, e to the x. At which point, what are we going to do with the e to the c? If you've got a 2 in every factor of an equation, what do you do with it? You cancel it out, right? Divide by 2. So divide by e to the c, which can't be 0, by the way. We talked about that already. Gone, right? So why bother? So the point is, well, rather, let's just put back to here. It's like, no need. It doesn't help the method. It doesn't add generality. Now, in principle, when you're thinking through a method of differential equations, you should add the c, and you should come to an understanding of why it doesn't matter. But now that we've had this conversation, we don't need to add the constant for the integrating factor, okay? Anyway, so let me clean it up. We've got e to the minus x dy dx minus e to the minus xy equals, this is just 1, right? Can anybody tell me what the deal is there? Like, can you tell me what this is? Can you simplify this? This is d dx of what?
E to the minus x times y.
Right. So that's by the product rule, right? I mean, the product rule usually goes this way, right? So the step we just made, I usually call the product rule in reverse, right? It's the unproduct rule. And that will also be true over here, right? Because what's IP? IP is di dx, right? So this is also the reverse product rule. It's d dx of I times y. That's not an accident for example 3. That's an inescapable fact. That's why we're multiplying by this mysterious integrating factor, because it forces this to happen. It is a sneaky trick. Okay, but of course that's equal to 1, and now how do you solve it? Now that we got to this, we have a total derivative is equal to a function. How do you get rid of the derivative? So the natural enemy of differentiation is integration, right? So we just integrate both sides. Now, I will tell you, adding a constant matters. You're like, make up your mind already? Well, you have to think. I mean, I'm sorry, but that's just kind of the nature, right, of the problem, is that here we have to think. But this is a indefinite integral. There's a constant added there in principle. And so my sort of generic solution then is y is equal to 1 over the integrating factor, the integral of the integrating factor times q dx. Oh man, I just solved all your homework problems. Look at that. That's the solution for every linear first order differential equation with nice enough p and q. It's right there, I boxed it. I'm joking. You actually have to work it out, right? So you're like, all I have to do is memorize that boxed formula. No, that is the opposite of what you need to do. What you need to do, and this is generically the case, if I go through a proof in here, there's a reason for me going through a proof in here, right? I don't like talking to myself. If I'm going through a proof, it's because I'm illustrating a calculational technique. That is almost universally the case in here, right? There are theorems I should prove in here which don't help you calculate, but I'm not so foolish as to try to prove those in here. Or ever, mostly, but all right, anyway, so over here, we have e to the minus x y is equal to x plus a constant. I have to add the constant when I integrate, right? Now I could put a box around it. What did we just do? We found implicit solution, right? I'm greedy. I want more than an implicit solution. I want an explicit solution. So what do I do? What's the explicit solution here? Solve for y. How do you solve for y? Multiply both sides by e to the x, right? And there you go. This right here is the explicit general solution. Any questions? Let me just, sometimes things go badly if I don't look up an example to do. If I make one up myself, there's no telling what might happen to us, you know. This is a good one. We'll do dy dx. Why don't I do something a little bit more interesting? How about this? We've got a voltage source, right? We've got a switch. We've got a resistor. We've got an inductor, right? And then we close the switch, time 0. So once the switch is closed, what does Kirchhoff's voltage law say? You electrical engineers, you can tell me, right? If I say I is like this, right? If this is resistance, if this is inductance L, what's Kirchhoff's voltage law says? It says E, what? I'm supposing that's constant, all right? If you'd like, we could make it a sinusoid, whatever. I'm going to keep it constant, just keep the math not too bad at the moment. E what? E minus what? IR? What's the voltage dropped on an inductor? No one knows. You guys have not had Physics 232? But like DC-AC? No one knows about RL circuits? LDIDT? Right. So this is Kirchhoff's voltage law, or KVL. As you can see, it's a first order differential equation, right? And so I can rewrite this in standard form, d I dt, plus R over L, I, is equal to what? Equal to E over, I may have a sign wrong here. I'll tell you just a second. E over L. I probably have a sign error here. I mean, this differential, we should get this differential equation, I think. So that means that I was supposed to have minus L di dt here. Sorry about that. Yeah. I haven't taught 232 in a couple years. I'm getting rusty. My bad. All right, so R and L and E are constants, okay? How do we solve it? Sorry, mathematically I'm being rather boring here. It's almost the same problem we just worked. It's like example 3. except instead of having an interesting function like e to the x, I've got a boring constant function, just e over L, right? So integrating factor would be e to the minus r over L t, right? Multiply this by e to the minus rt over L di dt plus r over L e to the minus r over lt times I equals e over L e to the minus rt over L, right? Reverse product rule. All right. We have ddt of e to the minus rt over L times I is equal to e over L e to the minus rt over L. Now if we integrate both sides, what happens? With respect to time, of course. On the left-hand side, I get e to the minus rt over L times I times the current. Now, how do you integrate e to the something? If I have integral of e to the alpha t dt, what's the integral? But if I differentiate this, this gives me alpha squared e to the alpha t. So that can't be the antiderivative. You're differentiating. It's cool, but we need 1 over alpha. 1 over alpha. So here, the alpha is minus r over L, right? So I get minus L over r. That's my 1 over alpha. And then I have e over L, e to the minus rt over L plus a constant. The L's cancel, which is good for dimensional reasons. And I can solve for I of t, I as a function of time, that is equal to c, oh, shnikes. Huh. Phooey. Yeah.
Is this supposed to be e to the negative r over lt?
Oh, thank you. And so this is the danger in not thinking, right? If I actually, and this is actually just like I planned it, so perfect. No, actually, this is a teaching moment. I'm trying to teach. Let's see here. And so it's good that I make a mistake in this case, because right here, this is bogus. Right? What happens when you actually differentiate the bottom? What do you get? You get minus, right? Differentiate this. We get minus r over L, exponential I, plus e to the exponential di dt. Do I have a minus in the step above? I do not, right? So if I had thought through that, I would have discovered the mistake. There's a redundancy built into this calculation. That's why we go through these steps and we don't just memorize this formula. If you just memorize this formula, you don't get this redundancy check. Because if the reverse product rule doesn't happen, what that means is that you calculated the integrating factor wrong, as I did here, right? So here it was a simple enough mistake. That should have been what? That should have been plus, right? Which makes this a plus, 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 which makes that a plus. All right, but also, because I was about to analyze the physical reasonableness of my solution, and I was getting a current which blows up to infinity as time goes to infinity. This is very disconcerting, right? I mean, we would like the current to drop to 0 after the inductor is charged. wait a minute, no. We would like the current to do what? After the inductor's charged, it should just be I over R, right? E over R. After a long time, inductors look like short circuits. That's what you learn in DC, AC. Or whatever you guys call that course, I don't know. Anyway, so we get C, e to the minus RT over L, plus E over R, E over R, because that cancels. And there you go. As you can see, as time goes to infinity, what happens? E over R, the steady state current. It's as if the inductor is not there and we just have Ohm's law on the resistor. I believe some of you are electrical engineers. This should be your happy place, no? I don't sense happiness. That's because you're not all electrical engineers. And this is the reason you didn't choose electrical engineering, isn't it? Yeah, I know. All right, I will stop with this. I realize that 232 is not a prerequisite for this course. I'm just doing this for the sake of application, right? In contrast, 231 is a prereq, and I will test on physics and tests, like kinematics, dynamics, mechanics. This is really not so much. I mean, if I ask a question about electricity and magnetism on a test or something, or a quiz, it's going to be very much like one we did in class. I wouldn't expect you to like do further physical analysis, let's say. It would just be the mathematics that you've already done. Okay, enough about that. So that's the integrating factor technique. And now, move on to number 3, exact equations. Let me get some of my juice. Do you guys remember Green's theorem? What did Green's theorem say? I know you had calculus 3. You can't pretend that you never saw Green's theorem. It's not allowed. So let me remind you. So it concerns some region R, right? And the counterclockwise oriented boundary of the region. The boundary of R, right? So simplest form of this is when R is simply connected, meaning that it's got no holes, right? Simply connected. So what did Green's theorem say for such a region? I need to throw this thing out. It doesn't really work. It keeps wasting my time. Maybe you remember this. The integral of, what was it? P dx plus q dy. What was it equal to? On the boundary of R? Was equal to what? Was it partial q, partial x? Minus partial p, partial y? Is that right? Let's see here. So I'm reminding you this, guys, because we're going to need this in a bit. See here, so I'm going to just put that up there. And now I need to share with you a little bit about level functions. So consider f of x comma y equal to some constant, right? This is a level curve, right? We defined something called the total differential in Calculus 3, right? What would that look like? Say df is partial f, partial x dx, plus partial f, partial y dy, right? Now, in the context of a level curve, what's this also equal to? 0, right? So here's basically the method of level. Here's the method of exact equations. All right. If m dx plus n dy is equal to the total differential of a function, then f of x comma y equals to a constant solves star. Well, let me not. Solves m dx plus n dy equals to 0. So this is the method of exact equations. So what I'm saying is if you can, now this right here, you'd be like, what are you talking about? I mean, what is this? This is what's called the Pfaffian form of an ODE, my first order ODE. O is for ordinary. DE is differential equation. Ordinary just means that there's one independent variable. We talk about partial differential equations, which have more independent variables much later in the course, okay? So everything we're doing is ordinary for a while, for the most part. It is somewhat hypocritical for me to say that everything we're doing is ordinary when I just talked about a function, two variables over here, but it's different. I shouldn't say that. You wouldn't have thought if I hadn't said it. Oh well. Okay, so this is the Pfaffian form. Now, for example, what am example on? 5. You may still be wondering, why am I talking about Green's theorem? I'll get back to that. Example 5. How about this? If we have dy dx equals to minus x over y, this is a good, I mean, admittedly, we could use separation of variables, right? Fine. You got me there. Don't disagree. But this is a useful example for us for exact equations as well. So if the differential equations looks like, so I would, let's say this is, let me say that this is related to the following one. This is related to like y dy equals to minus x dx, or better yet, x dx plus y dy equals to 0. Now, technically speaking, these are not the same differential equation. What's the difference? I mean, the differential equation I boxed in black is not defined. What's the domain of definition for the differential equation? Certainly y equals to 0 is not allowed.